How's it going, guys? Let's have a look at 1589. We have two billiard balls A and B. They are originally in contact with one another when a third ball C strikes each of them at the same time as shown. Alright. If ball C remains at rest after the collision, determine the coefficient of restitution. Now, importantly, all the balls have the same mass. And they say neglect the size of each ball. Okay, neglect the size, but it's important. Our assumption also is that they have the same diameter. That is key. So they have the same mass. And my assumption here to solve this problem, although they don't say it, is the same radius, the same diameter. Okay? So now, we are looking for the coefficient of restitution. It looks something like this. V, I want to say V, whatever the second object is, it's VB2. Don't ignore these. I'm just giving you an idea. Ignore these letters here. The final velocity of the one particle minus the other velocity divided by the initial velocity of the one particle and minus the other velocity. Okay, that's the idea. That's what we're looking for. All right. So what tools do we have in our bag to try to find something like this? Well, if we're looking for the coefficient of restitution, we need velocities after and we need velocities before. That's kind of the idea that we need. And it's between two particles. So as you can see, we have a ball and it collides with a single ball, collides with A and it collides with B. Okay, so how are we going to deal with this? The coefficient of restitution is between, say, C and A or C and B, right? Okay, so I hope I'm not confusing you too much yet, but this is kind of the idea that we need some velocities and we need to analyze two particles that are colliding, either C and A or C and B. Okay, so one tool that we have in our bag is conservation of momentum. So if we consider this as our system, we have C, A, and B. Let's just write it out. Conservation of momentum. We know that what happens is ball C is traveling with a certain momentum. Okay, it collides, it impacts A and B at the same time, and even at the same kind of angle from this horizontal line. And it is afterwards, after collision, it is at rest. So all its momentum is transferred. Okay. So we have the mass of C, velocity of C at 1, plus the mass of A, velocity of A at 1, plus mass of B, velocity of B at 1, equal to, believe it or not, the mass of C, at velocity of C at 2, etc. Okay? Velocity of A at 2, plus the mass of B, velocity of B at 2. Alright. Now, you're saying, okay, why did you write all of that out if they've got the same masses? You're 100% correct. So mass of C, mass of A, and mass of B is the same. So we can drop those subscripts C, A, B. These three masses are identical. But now we need to kind of ask ourselves, okay, what exactly is happening? This particle C, ball C, is traveling in the horizontal direction with a velocity of V. It impacts it along that line, and so we can say that it impacts both A and B at the same angle to the horizontal. The one will be an angle above the horizontal and the other one will be the same angle below the horizontal. So if we look at these three, okay, just imagine they're touching. Okay, what's this angle here? We have what do you guys call it? I haven't done this in years. It's an equilateral triangle. So I think these are 60-degree angles. So that angle that it impacted at is 30 degrees. Okay, that angle is 30 there. Okay, and the angle below is also 30. Okay, so what's going to happen is this ball is going to travel at V in that direction. It's going to impact it, and we are going to have this ball A then travel at VA2 after impact, and this ball B travel at VB2 after impact. Okay, so we have an initial momentum of C. Ball A and ball B are both at 0 velocity, so they have 0 momentum. And then after impact, ball C is at 0 velocity, so it has 0 momentum. So we can rewrite this as mvc1 is equal to mva2 plus mvb2. Okay? Because of the 0 momentum before and 0 momentum after of these particles. Now, what we need to see here is because it has the same mass, they collide at the same angle, VA2 and VB2 are going to have the same magnitude. Obviously, they're moving in different directions, but VA2, the magnitude of VA2, let's do that, is the same as the magnitude of VB2. Okay? So VA2, VB2, it's the same. But if we just consider what's happening in the x direction, we're going to have something that looks like this. MV, and we can call this dash, okay? V dash, that, and we're going to also have the same mass moving in that direction, V dashed. But I made a mistake here. We're just looking in the horizontal direction, so that's an angle of 30. So we're going to have M times V dashed cos 30 plus this mass times this velocity, which is V dashed cos 30 as well. Because we're just looking in the horizontal direction, so we need the component of this velocity and the component of this velocity in the x direction. So this is going to be mv, because that is the initial velocity of C, equal to this, and we end up with mv is 2mv dash cos 30. Okay. I hope you're not too confused at this point. Alright, so we've got that, but we're still looking for the coefficient of restitution. So remember, the coefficient of restitution is between two particles that are colliding. So we can choose particle C and particle A. Alright, let me just break that there. So E is equal to, and I'm just going to write it out like this, the velocity of A2, right, minus the velocity of C after impact. Okay, so velocity of C before impact and velocity of, this is velocity of C after impact, divided by the velocity of C before impact, 1, minus the velocity of A before impact, 1. Alright? But we know that velocity of VA2, we said VA2 is equal to VB2, so we'll call it V dash. Okay? So that becomes just simply V dash, because now we are considering this line of action, okay, because that's our line of impact between C and A. We're considering just that line of impact now. Okay, so A is going in that direction. So VA2 is this V dash. VC2 we know is 0 because it came to a halt after impact. And VC1, because we're looking at oblique impact, we need to consider this V but moving in this direction. So that would be V cos 30 as well. Okay, V cos 30, so this is V cos 30, it's the initial velocity of C along this line of impact. And we know that VA1 was 0. Okay, so E is V dashed over V cos 30 But what is V dash? If you solve this, I'm just going to rewrite this. As you can see, these masses cancel. So we've got V is 2V dash cos 30. Okay? If you solve for V dash, you're going to get V dash is V over 2 cos 30. And so we substitute this in there, and we're going to get V over 2 cos 30 times V cos 30. The V's cancel. We get 1 over 2 cos squared 30. And if you solve this, you're going to get 2 over 3. So the coefficient of restitution between C and A, or between C and B, is equal to 2/3. Okay? I hope this makes sense, guys. And I really ask you to please not memorize a problem like this. Do not memorize, because if you memorize and we throw something different at you, then you're just lost. Learn to pick up the principles. Use the conservation of momentum. I used coefficient of restitution. What is coefficient of restitution? What is the concept behind coefficient of restitution? And as this collides, what happens? What are the directions of these balls? In what direction do they move? What's this angle? Okay, the masses are the same, so we drop the subscripts. These velocities were the same after impact, albeit in different directions, and we just looked in the horizontal direction. Okay, so please learn principles, learn concepts that you can apply to different problems. Cheers.